Hi everyone, my name is Raquel Ortasun and I'm the Chief Scientist at UberATG, as well as a professor at the University of Toronto. Today, I will talk about approaches that perform human perception and motion forecasting in the context of self-driving vehicles. The traditional software stack for self-driving is composed of a set of models executed one after another. Every fraction of a second, the vehicle senses the environment. This is illustrated here with a bird's-eye view of the LiDAR point cloud. The first task is then to localize the vehicle with precision of a few centimeters. This is done not only to route the vehicle to the desired destination, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene, here depicted with rectangles for vehicles and circles for pedestrians. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as friction and simplistic vehicle dynamics. This full process is then repeated every fraction of a second, typically 100 milliseconds. The advantage of this popular paradigm lies in the fact that we have interpretable intermediate representations and it is easy to incorporate prior knowledge. However, reaction time is typically large as computation adds up. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for those changes. Furthermore, the different models are not trained for the end task, and thus improvements in model performance do not translate to better driving. Our vision, which is different from any other competitor, has the advantages of both end-to-end and traditional engineering approaches, but without inheriting the respective drawbacks. In particular, we believe in having a single AI system that can automatically adjust itself to any changes, thus increasing significantly developer productivity. As computation is not shared across modules, the resulting reaction time is also much lower. Furthermore, we produce interpretable intermediate representations and allow for the incorporation of prior knowledge. For example, to guarantee that we follow the rules of traffic. And finally, since our approach is trained for the end task, every improvement results in better driving. Let's get back first to the traditional self-driving pipeline, where once the objects are detected and tracked, we need to predict the future trajectories for our actors in the scene. The simplest method to tackle this problem is to enroll the tracker state with a kinematic model, such as a constant velocity or constant turn rate and acceleration. Another option is to perform maneuver-based prediction, where first the intent of an actor is classified, and then we can either use a fixed set of prototypical trajectories for each intent, particle filter, or other approaches to obtain the final trajectory. The main downside with this traditional pipeline is that the information that gets passed into the prediction about detection and tracking, as well as the static environment, is very compact, with many inherent assumptions, and thus a lot of the information has already been lost. To fix this, let's see how more recent works have tried to use neural networks to learn more flexible representations. There are many representations that were originally designed for detection that can be used for the task of motion forecasting. Waypoints of past trajectories, together with their uncertainty, if available, can be passed through an RNN encoder. Some works have also leveraged voxelized LiDAR in a local region around the perceived actor to account for geometric cues. A better option is to rasterize the geometry of the perceived traffic participants in a multi-channel bird's-eye view image local to the actor, to each actor, and use a CNN on top to extract actor features. For the environment, map rasterizations have also been explored. Recently, approaches that exploit the relational information in the map together with graph neural networks or transformers have also been proposed. Let's look at our latest work on exploiting lane graphs. The map data is represented as a set of lane segments and their connectivity. Each lane center line is given as a polyline, and 4 types of neighbors are defined for each lane. We use each line segment of the polyline as a node in the lane graph. For each node, We derive its connectivity based on the neighbors of the lane segment in the map they belong to. Our approach is then composed of three modules. ActorNet applies one-dimensional convolutions to encode past trajectories of actors and outputs actor features. MapNet is a multi-resolution graph neural network that exploits the lane graph and computes features for each node. We then fuse the actor and lane features with custom graph propagations. Finally, the prediction header regresses multiple feature trajectories and their corresponding confidence scores for each actor. Our model performs state-of-the-art in the Argoverse motion forecasting benchmark. Importantly, our results was submitted 3 months ago to the leaderboard, and it still has the best multimodal minimum average and final displacement error, despite the fact that there was a competition with prices in between. While this great performance is exciting, the Argo-based dataset assumes that the input to the prediction system is perfect perception, which is never the case in practice. To tackle the real problem, in the past 2 years, we have developed many approaches to perform joint perception and prediction. This has many advantages. It lowers significantly the reaction time, enables much higher developer productivity, and produces richer representations that still preserve the interpretability of both tasks. We are now going to review these approaches, providing you insights into why each model was developed at the time. Our work, Fast and Furious, was the first approach to show that it is possible to unify both tasks, and it appeared as CVPR 2018. The input is a history of previous LiDAR sweeps. Using the pose of the SDB at different timestamps, we can project past sweeps to the current coordinate frame. We can then voxelize the point clouds into a bird's-eye view tensor with 4 dimensions: height, width, time, and depth. We employ 3D convolution using depth as features to fuse the spatiotemporal information. Once the time dimension has been reduced, we can predict the outputs with a 2-dimensional convolutional header. In particular, for each pixel in the output map, we predict a classification score and a series of future waypoint regressions. The final prediction is obtained by using NMS, followed by indexing the regression tensor at the positive locations. In this video, we show the LiDAR point cloud together with the detection scores, bounding boxes, and the short-term motion forecast for 1 second into the future. The vehicles are color-coded according to a heuristic tracker that matches detections to previous motion forecasts in a post-processing step. Not how difficult the task of driving is, how many actors there are, and how accurate the predictions are. Maps are an important prior for both detection and prediction. For instance, it is more likely to find a vehicle on the road than in the sidewalk. A vehicle probably will most likely keep its current lane in the future. In IntentNet, we propose to raster the map in bird's-eye view and extract features with a 2D CNN, which can then be trivially fused with the LiDAR features coming from the other stream by concatenation along the feature dimension. Here, the LiDAR CNN is simplified to a regular 2D CNN by stacking depth and time together in the input, which uses better performance and is much more memory efficient. Moreover, we show that we can also accurately predict discrete intentions by adding yet one more header that performs multi-class classification over actions such as turning right, stopping, being parked, or lane changing. This allows the planner to not only reason about occupancy, but also about semantics. The outputs of the network are split into 2 visualizations. On the top, we can see the same output as in Fast and Furious. And in the bottom, we show the high-level actions prediction, which provides a more interpretable way to see the driver's intention than just future trajectories, using for motion, which are actually very useful, these intentions for motion planning. More precisely, this gives us the probability of a car being parked, stopping, keeping lane, lane changing, or turning. A purple bounding box means our model believes the vehicle is parked. The redder it is, the higher the probability of stopping. We visualize the likelihood of keeping lane, turning, or lane changing by the length of these arrows. We evaluate our approach in our challenging ATG4D dataset. This dataset contains over 1 million frames from more than 5,000 snippets collected across multiple cities in North America. It provides point clouds from a 64-beam radar sensor and high-definition maps. It contains very challenging urban incidents with many actors, making it interesting for agent-to-agent interactions. Fast and Furious and IntentNet set a strong baseline for follow-up works. IntentNet's architecture with map fusion improved detection mean average precision by 6 absolute points. Reduced the final displacement error at 3 seconds into the future by 20%. And improved the interaction understanding of the motion forecast, improving their consistency thanks to a bigger receptive field. We measured this by computing the percentage of collisions among the predictions of different actors, with lower being better since there are no collisions in our dataset. Finally, it can predict the vehicle's high-level action with a 71 F1 score despite the high imbalance between categories such as keeping and changing lane. FAF and IntentNet use a joint model to solve detection and prediction simultaneously, but perform object tracking as a post-processing. As a result, the full temporal history containing tracks is not used by neither detection nor prediction. To remedy this, PMPNet brings explicit object tracking into the loop so that all tasks can benefit from rich temporal context. PMPNet will be showcased at this year's CVPR. So PMPNet works as follows. We first perform 3D object detection from radar and HD maps. We then associate detections across time and smooth their trajectories by exploiting fully learnable functions. Finally, we extract long-term trajectory level features from motion forecasting. To keep track of objects under occlusion, we equip the model with an explicit memory, capturing appearance as well as inferred trajectories. In these snippets, the self-driving vehicle is located at the left center, and we show the perception and prediction results of PMPNet on vehicles and pedestrians within 100 meters. Different colors denote different object identities. We visualize only high confidence detections at each frame to avoid clutter. On 2 large-scale benchmarks, PMPNet achieves a 2% gain on detection, 8% gain on tracking, and up to 20% improvements for motion forecasting. However, these approaches are not trained for the end task, that is the task of driving. Next, let's look at the first neural motion planner that produces interpretable representations. Our first attempt was NMP, which was presented at CVPR last year. It utilizes a common backbone to extract useful information from radar point clouds and HD maps, and several headers to perform perception, prediction, and motion planning. The planning header utilizes a simple deconvolution network that takes the backbone feature map and outputs a cost volume. The value of each pixel in this volume represents the cost for the ego car to be at that location at P2 timestamp, where different timestamps are encoded with different channels. During inference, we use a physically valid trajectory sampler to sample a wide variety of trajectories. These trajectories are guaranteed to follow vehicle dynamic constraints. We then evaluate the cost of each trajectory by simply indexing the cost volume. We train our model end-to-end with a multitask loss, including detection, prediction, and motion planning losses. For detection and prediction, we use standard classification and regression losses. For planning, since we do not have ground truth supervision for the cost volume, we utilize imitation learning and encourage trajectories to have low cost if they are close to the expert demonstrations. We also penalize trajectories that collide with objects or do not follow traffic rules. Here we show our results. Compared to the state of the art, our model achieves better detection and prediction performance. Our planning results have a much lower collision and lane violation rate, which indicates safer planning. Let's look at qualitative results. Our model takes radar and HD maps as input and outputs detection, prediction, as well as the motion planning cost volume. We highlight low-cost regions for different timestamps using different colors. Our planned trajectory is shown in red, and the ground truth trajectory is shown in blue. As we can see here, it follows the lane perfectly. Note that our cost volume captures multimodality. In this case, we can either go straight or change lanes. When approaching an intersection, we can either keep lane or turn right. We can also handle blockages. The cost value shows a preference to lane change in order to avoid collision. Here are two examples of super nudging in heavy traffic, one of the most difficult maneuvers in self-driving. Note that while I'm super excited about our neuromotion planners and our novel approaches to do so, in this workshop, I will focus on joint perception and prediction, and refer to the workshops in the slide for other talks where I'm going to describe unpublished work in neuromotion planners. The models we have presented so far do not do any interaction reasoning. Let me try to illustrate why this is important. In this scenario, we can see two cars reaching an intersection with no evidence of any of them braking. If we have a model that just looks at the local road topology and the past motion of each actor independently, the most likely prediction is just the extrapolation of the previous motion, ending in a collision despite our belief of this event to be highly unlikely. But can we instead explicitly reason about the interactions between them by taking into account the relative locations, speeds, and the context of the intersection when predicting? This will be achieved by exchanging information between actors to make more informed inferences, such as predicting that the car on the left will most likely yield. Now let's see how we can model these interactions in practice. Several works propose to use social pooling techniques, that is, under some definition of neighborhood, to take the features from neighboring traffic participants and scatter them into a spatial social tensor, potentially running a small CNN on top to further process these features, and finally performing average of mass pooling on the spatial dimensions to obtain the so-called social feature vector. However, as can be seen in the model diagrams, these social tensors are dense, meaning that even if the neighborhood is sparse, they still need to be computed. Thus, a lot of computation is wasted, since these dense social tensors are produced for each actor in the scene. An alternative attention-based approach has also been proposed in CARNet. It consists of attending to a spatial feature map that captures a static environment and dynamic actors. This feature map can be obtained through a CNN that processes a later input stream, for instance. Then CARNet uses a combination of single source attention to focus on the most relevant aspect for the target actor, and multi-source attention to take into account the scattered features that might also be relevant. For instance, you could imagine in the simple car following behavior, the most important cue is the speed of the car in front, but the road geometry also matters. To do so, we can extract features from later maps, as we have seen before, and fuse them. Once we have rich features from the whole scene, we can obtain object detections shown in red. Let's focus on one of the vehicles. Since we know the information ahead and to the side is the most relevant, we attribute this region of interest to the actor. Then we can pull the features on that region as the summary of the actor characteristics. We can do this process for all vehicles in parallel. We can now further propose the features with a CNN with global pooling and obtain a feature vector for each actor, which is passed to the prediction model. These three methods assume perfect perception in their papers, or in other words, that the ground truth path trajectory is given. However, this is not realistic in self-driving cars, where we must operate with a real, noisy, uncertain perception system. To keep their model unchanged, one option is to extract past trajectories using an off-the-shelf tracker that consists of an unscented Kalman filter and Hungarian matching on top of object detections from the past frames. A better option is to replace the past trajectory encoders in these methods with our feature extraction pipeline and train the model end-to-end. This brings a big improvement over the traditional pipeline based on tracking that is not optimized jointly. In particular, by using joint perception and prediction, we see reductions of an order of magnitude in the collision rate among predicted trajectories from different actors. This shows that the initial hypothesis that the traditional pipeline passes too compact passes to compact information to prediction is actually true. And thus optimizing end-to-end yields better results. One aspect that is hard to handle for the traditional pipeline is missing data, which we encounter when either a vehicle was not detected in the past or the track was fragmented. We take this interaction modeling one step further and propose a spatially aware graph neural network that aggregates neighboring features through message passing in an interaction graph where each vehicle is a node. We find that in the messages, it is important to pass the information in a relative coordinate frame to the heading of the receiver's node. Finally, we characterize the marginal trajectory distribution of an actor by predicting a Gaussian trajectory for its updated features from its updated features from the graph propagation. Here we ablate the interaction operator by using the exact same backbone network architecture and feature structure in our models. We can see how our spatially aware graph neural network improves the final displacement error by around 10%, and it has less than half the collision rate of other approaches. Before moving on, let's quickly check where this model stands with respect to previous joint perception and prediction approaches. We can see that the two-stage end-to-end architecture and the explicit interaction reasoning we just proposed, together with some improvements in the backbone network, bring major improvements across all metrics, particularly in interaction understanding. We compare our method qualitatively against the other methods we have talked about in a set of challenging scenarios with very fast-moving traffic. The ground truth trajectories are shown in gray, while the Gaussian predictions are shown in the color map ranging from blue at the current timestamp to pink at 3 seconds. We highlight collisions with a red circle, and as we can see, our model is the only one that produces a socially consistent prediction with low probability of collision. Our model is called SPY-GNN. SPY-GNN reasons generally about detection and relational behavior forecasting, taking into account interactions between actors. We design a spatially aware graph neural network to refine probabilistic estimates of future trajectories, providing uncertainty. This approach is very efficient and in practice only requires one parallel random message passing. The results look socially consistent, as expected from the explicit interaction reasoning, despite it being just trained with Gaussian negative log likelihood without any explicit collision loss. The main failure mode of this method are intersections or branching points, where the unimodal Gaussian output can handle the multi-modality in the expected behavior. So that's our next focus. As we've seen so far, our perception and prediction efforts have focused on how to learn powerful representations from sensor data and how to optimize both tasks jointly. However, capturing the uncertainty and multimodality trajectory distribution of an actor is key to safety and autonomy. If we look at the diagram below, the vehicle is on a road where it can go straight or turn left. Therefore, the underlying ground truth data distribution contains different speed profiles for these two high-level actions, as shown by the black arrows. We illustrate the prediction of 3 models. On the left, an accurate model closely characterizes the distribution of trajectories. In the middle, the model prediction covers the ground truth distribution, but we also see unrealistic samples. We can say this prediction has high recall but low precision. On the contrary, the last model has very low entropy and only covers one of the modes in the ground truth distribution, exhibiting high precision by low recall. In the next slides, we will see that the trade-off between precision and recall is key for safety. In practice, in real-world data, there is an additional challenge because we don't have access to the underlying ground truth distribution, since we only observe a single realization of the future. Let's look into what methods are out there to capture these complex distributions. The simplest way to capture this multimodal uncertainty is to have a mixture of Gaussian trajectories. Basically, a predefined number of modes, where each mode is a sequence of bivariate Gaussian waypoints over time. However, training directly with this negative log likelihood tends to be unstable, probably because of the fact that we only observe one of the modes in the ground truth, and the modes can be very far apart as the prediction horizon grows. This can be mitigated by only training with the likelihood of the closest mode, clustering the training distributions into anchors and predicting offsets from this, and finally reparameterizing the discrete latent variable and using variational inference to optimize the mixture. Another natural way to capture multimodality is through occupancy grid maps. These approaches discretize a local region around the actor into bins, as shown in the left image, and then predict a multi-class classification over the grid cells at each future time step. Since each cell encodes the probability of the actor being there, it is inherently multimodal. Basically, to predict a multimodal distribution, the model just needs to place probability in different grid cells. This can be appreciated in the results of our discrete residual flow model on the right, which can reason about the environment very accurately, avoiding parked cars and following crosswalks and sidewalks. As opposed to Gaussian mixtures, the classification laws of these methods make optimization very stable. However, this is a very memory-consuming representation, since we predict a dense grid for each actor at each time step. Another classification-based approach are trajectory sets. Basically, a finite set of trajectories is defined, and the problem becomes a multi-class classification over these trajectories. This has the great advantage that we can easily incorporate prior knowledge into the trajectory set. For instance, guaranteeing feasible vehicle dynamics. Examples are shown in the figure, where different sets of trajectories are used at different instantaneous velocities. On the other hand, the number of trajectories needed to ensure coverage of all the possibilities is very large. Instead of attempting to capture the marginal distribution of future trajectories, we can instead model the one-step conditional distribution. Basically, what's the distribution over waypoints at time step t+1 given a sample trajectory up to time t. This has the advantage that a simple unimodal and well-known distribution such as a Gaussian can be used to model each step. Through sequential sampling, this method can achieve multimodal trajectories if the interval between two timestamps is small enough. However, sequential sampling is slow and suffers from compounding errors, also called distributional shift. This is because during training, the model is conditioned on the ground truth trajectory up to time t, but at inference, it is conditioned on a sample trajectory coming from the model, which can be actually quite different. Even though we can train our models with symmetric losses such as L2 and Gaussian negative log likelihood and obtain multimodal uncertainties, these losses do not reflect well the impact on the downstream tasks of motion planning. This is because the decision-making in a self-driving car is normally very structured, particularly relying on the map topology. Let me illustrate this with an example. The green trajectories represent the ground truth future behavior for the blue vehicle, and the red and blue trajectories are two predictions that have the same exact L2 loss, yet have very different impact in planning. In the left figure, if we predict the red trajectory, it will cause the SDV to swerve out of the road to avoid collision. In contrast, predicting the blue trajectory wouldn't have any impact on autonomy. A similar story holds in the right image, where if the red trajectory is predicted, the self-driving car will think there is no obstacle in front and could accelerate and get too close to the blue vehicle, causing a future hard brake. Based on these insights, we first extend the Spaginian model I presented before to be able to capture multimodality by predicting a mixture of Gaussian trajectories. Then, instead of just training it with the negative log likelihood of the closest mode, we incorporate our prior knowledge about the reachable lanes and the self-driving vehicle route. More precisely, we can associate each vehicle to a lane and obtain its reachable lanes, shown as the green shaded areas. Then we can reward predictions of the staying within such an area and penalize going outside of it, like the red trajectory in the top left. There is an exception though. Since some actors behave in a non-compliant manner, as in the top right drawing, and we want our model to still capture this behavior, we do not apply the prior loss when the ground truth doesn't follow the reachable lanes. Finally, we can similarly reward high precision and recall of vehicles driving closely to the self-driving vehicle route making the distinction of being inside versus outside of it. Then we frame our prior loss as the negative expected reward. Despite the fact that it's not differentiable, we estimate the gradients using reinforce and approximate the expectation with Monte Carlo sampling. To evaluate the map understanding, we can compute the final lane error by checking if the final waypoint at 5 seconds into the future falls inside or outside the reachable lanes. We do this for 50 predicted samples and the ground truth, and check the percentage of times they disagree. We only evaluate on moving objects since the static ones are trivial, and break down the results by high-level action. We can see our method shows gains over previous approaches. In particular, it is worth looking at SpyGNN Plus, which is the SpyGNN extension to predict a mixture of Gaussians. In other words, our exact same model, with the only difference that it doesn't have the prior loss. Next, we evaluate the precision and recall of our samples. The mean average displacement error, or mean ADE, measures the expected displacement error across samples, being a proxy for precision. In contrast, the minimum ADE represents the recall of the ground truth realization by measuring the distance to the closest sample, as shown in the diagram. We can see our prior loss heavily improves the precision of our samples, although it trades off a bit of recall. As we will see in a couple of slides, this trade-off will pay off. For now, I want you to keep in mind that minimum ADE is the commonly accepted metric for motion forecasting, despite the fact that it only measures a single sample, the best one. Here is a qualitative comparison of the same model without our prior knowledge loss on the top row and incorporating prior knowledge on the bottom row. The visualization blends 50 trajectory samples for each vehicle. The transparency denotes its likelihood, and the color map the prediction horizon, as can be seen on the bar on the right. We can see that the baseline produces unrealistic samples going out of the map. In contrast, our model produces a realistic lane following behavior for the same two cars. Let's look at another example where a vehicle is going off the road. We can see how our model can capture this behavior as well as the baseline. Let's see what the public benchmarks are measuring. Here we show a screenshot of ArcoBest and Newsim leaderboards. We can see that most of the metrics are symmetric, based on Euclidean distance as highlighted in red. While they include a drivable area compliance or off-road rate, it seems like the set of metrics is still heavily dominated by Euclidean distance. Moreover, the recall metrics of minimum ADE and miss rate seems to be the most present, with ArcoBest ranking the submissions by miss rate of 6 samples. That is, the percentage of times the ground truth is not found within a 2-meter radius in the 6 most likely samples. Precision is only partially measured via map understanding, but the average ADE is not included. This encourages participants to obtain very high recall in their predictions without paying too much attention to precision, thus favoring higher entropy distributions, which might not be useful for driving. Leaving aside the discussion about prediction and recall for a moment, shouldn't we be measuring the impact of the detections and motion forecasts into the downstream task of motion planning? At the end of the day, this is where the outputs are going to be used. In this work, we use a state-of-the-art structured learnable planner to assess what motion forecasts are, to assess what motion forecasting methods are the most beneficial. This tries to bridge the gap between research in motion forecasting and production stacks, which already measure this. We found that our model with prior loss, despite showing slightly worse recall metrics, enables much safer motion plans with a 17% drop in collisions for the strongest baseline, and also a closer imitation of the human expert demonstrations. This shows that motion planning performance doesn't necessarily correlate with minimum ADE, and we think other motion forecasting approaches should start including more precision metrics and measuring the impact of motion planning. Here is an example on why the precision matters for safety. The columns correspond to different time steps of the unrolled feature horizon of 5 seconds. We show both the SDV motion plan and the other actors' trajectories. In blue is the SDV plan. In a black box, without filling the expert demonstrations, the prediction samples are shown in yellow and the ground truth trajectories of other actors in light gray, unless they are in collision with the SDV plan at any point, in which case we show them in red. Please focus on the vehicle of interest marked with a circle throughout the sequence. We can see how the predictions for the baseline gets more and more fan out over time, ultimately forcing the SDV to swerve into opposite traffic and collide. In contrast, when using our prior laws, both the predictions as well as the SDV normally follow the lanes, resulting in much safer behaviors. The changes of adding our prior laws are very evident. The distribution becomes less entropic and follows the map better, while still being able to capture non-compliant and off-road behaviors, as we will see in the next snippet. Here's an intersection with a different pattern. Here we see one more motion planning unrolled and posed to appreciate the difference of the free space around the self-driving car. We are now getting to the final topic of today's talk, the inconsistent samples. So far, we have seen how different models capture uncertainty and multimodality at the actor level, but this doesn't guarantee that if we sample from each of the actors independently, the samples will be consistent with each other. Let's look at an example. As we can see, there are two actors approaching the intersection. Assuming they have similar speed, then an independent output for each actor might look like the Gaussian uncertainty shown in the drawing. This marginals could be accurate characterization of the world when using a simple model, since the two prominent modes at the same level is that one car yields and the other one goes, or the other way around. However, what's not possible to do with this model is to get the same consistent samples. Since the output distribution for each actors are independent, when we sample from each of them, we might obtain inconsistent features like the one illustrated here, which results in collision. On the right, we show the behavior we aim for in another illustrative example. This is a situation where two cars come to a merge. The most likely feature is that is the one of the merging vehicle yields and the other one goes. Another possibility is that the driver in the yielding lane is aggressive and speeds up to cut in front of the other vehicle, which will then react. In any case, a collision scenario is very unlikely, so we would like our model to be able to produce such consistent samples across actors, or in other words, characterize the joint distribution over the future trajectories instead of characterizing the marginal distributions of each one of these actors independently. This will enable motion planning research that reasons about how to react to multiple prediction scenarios, as well as provide smart agents for simulation, since in a simulated world, we need to capture the dependencies across actor behaviors. So far, social autoregressive methods have been proposed to tackle this problem. Let's take a look. The idea is to condition the one-step conditional distribution for each actor, not only with their own past trajectory samples, but also with the ones from neighboring actors. In other words, the prediction at time t is conditioned to the samples of all the neighboring actors at time t-1, as shown in the graphical model on the right. This has the advantage that simple distributions can be used for the conditionals, and also that it's easy to make counterfactual predictions, where we ask how the trajectory distribution will change if we knew the trajectory of one or more actors. However, it implies a slow sequential sampling and suffers from compounding errors, also known as distributional shift, as we have seen before. Finally, all the approaches proposed using this paradigm assumes perfect perception which again we had discussed at length is not a good assumption, it's not realistic, and it will never happen in practice. To tackle the issue with this, with the social autoregressive formulations, we propose an implicit latent variable model that features parallel sampling of trajectories. The idea is to have a scene latent variable responsible for capturing the unobserved scene dynamics. In fact, we make this latent variable continuous and assume it captures all stochasticity in the scene. We adopt a distributed representation across actors in an interaction graph such that it scales to any scenario. Then a deterministic decoder can produce a consistent trajectory for each actor in the scene given a scene latent sample. Here you can see the graphical model in plate notation, which is fully connected and where the distribution of the output y is implicit from input x and latent z. This is our inference diagram. We extract actor features as previously discussed. We then have a GNN prior that infers the distribution over the same latent z. Then we can sample from the latent, and a deterministic GNN produces one realization of the future trajectories. We can then sample again to obtain a distinct future. Although I illustrate the sampling process as sequential for clarity, this sampling process is parallel since there are no dependencies between the different samples, thanks to the fact that all the stochasticity has been pushed to the latent distribution. This simple inference procedure outperforms all previous methods by a big margin on our dataset. Very notably, our method, ILBM, achieves 75% less collisions amongst motion forecasts in a scene sample than any previously proposed method, including social autoregressive approaches that in theory can characterize the joint distribution over actor trajectories. Let's go back to our illustrative example, but now showcasing actual predictions from our model at a four-way intersection. In the first possible future shown in blue, the traffic at the vertical and protected left turn at the intersection proceeds and the horizontal traffic stops. In the second possible future shown in pink, the vehicles in the vertical road are stopped and the ones in the horizontal road accelerate. In reality, these two futures are controlled by the future traffic light states at the intersection, which are unobserved. But it seems that our latent variable model manages to learn their underlying dynamics, including the fact that the traffic light state might switch in the future. Let's look at another scenario and compare to the baselines. In the first rows, we show multipath from Waymo and ESP. For both cases, the two most different scene samples out of 50 capture very low level variations at the actor level, corresponding to different goals or speed profiles, but with a single general mode at the interplay between the two vehicles facing the intersection. On the contrary, our method identifies that there is an interaction between the two vehicles at the intersection, and that the one on the left can yield to the one on the right, or vice versa. In this video, we sample 50 scenes and aggregate them using transparency to show the characterized marginal distributions. Quite surprisingly for us, our model not only achieves scene consistent samples, but a great understanding of the map despite having the same bottleneck network as our previous works. From our ablation, the deterministic decoder is the key for this success. By forcing the latent space to capture all stochasticity, we do not need to make independent assumptions about the joint trajectory distribution at the output level. Let me play this for a little bit. In conclusion, we have seen that joint perception and prediction outperforms the traditional pipeline, while still keeping the interpretability of detection, tracking, and motion forecasting. Moreover, we show that we can also do motion planning in this end-to-end framework. We have benchmarked multiple mechanisms for actor-to-actor interaction reasoning actors and proved this explicit reasoning to be beneficial. Regarding multimodality, we have seen that a trade-off between precision and recall in the distribution of trajectories is key to safety in motion planning. Finally, we have seen that it is possible to generate realistic scene-consistent samples efficiently with an implicit latent variable model. This is all for me today, and I hope you enjoy this history about all these different approaches in order to predict the future. Thank you.